Today, we're diving into the story of a physicist who basically set out to build a whole new kind of computer, one that runs on the bizarre, mind-bending rules of quantum mechanics. This is the story of John M. Martinis, the architect behind Google's groundbreaking quantum supremacy chip, and it's all based on a fantastic essay by Jörg Schneeppert.
That's right, and for this one, we're definitely going a little deeper than usual. So get ready, and welcome to our Quantum Deep Dive.
All right, so here's our roadmap. We're going to follow Martinis' quest right from the beginning, forging the very first qubits, hitting that huge transmon breakthrough, all the way to the finish line of Google's quantum supremacy moment, and finally, what his lasting legacy really is.
So let's get into it. Section 1. A Quest for Quantum. Look, in the grand story of building a quantum computer that actually works, John Martinis is, without a doubt, a central character. He jumped into a field with this absolutely monumental goal, to build a machine that could completely redefine technology as we know it.
And that's not just hype. The stakes here are enormous. Quantum technology is expected to cause these fundamental shifts everywhere, in science, in business, in all of society. We're talking a revolution on the scale of the first digital computer, and that was the challenge Martinis decided to take on.
So what is this quantum promise we always hear about? Well, these computers just work differently, They let us solve certain kinds of problems exponentially faster. We're talking about things like cracking modern encryption, discovering new medicines by simulating molecules from the ground up, or solving these insane optimization problems. All stuff that is basically impossible for even the biggest supercomputers we have today.
Okay, so that brings us to Section 2, Forging the First Qubits. Our story really gets going at UC Berkeley, which is where Martinis started laying the foundation for, well, pretty much his entire life's work.
And that foundation? It all starts with something called a Josephson junction. You can kind of think of it like a tiny, tiny sandwich made of superconducting materials. And it's this little device that lets you control quantum effects. Martinis literally dedicated his dissertation to mastering these things because he knew they were the absolute key to building a working quantum bit, or, as we call it, a qubit.
Now, if you want to build a quantum computer, there's this one incredibly special and unbelievably delicate property you have to control: quantum coherence. Coherence is the magic sauce. It's what lets a qubit exist in a superposition, being both a 0 and a 1 at the exact same time. All the computing power comes from this. But, and this is a huge but, this state is so fragile. The slightest little whisper from the outside world can make it all fall apart.
And that right there is the core challenge. When a qubit is in a coherent state, it can hold just a mind-boggling amount of information. But the second it interacts with the noisy outside world, decoherence happens. The quantum magic just vanishes. Poof, the superposition collapses, and your powerful qubit becomes just a boring old classical bit. All that incredible computational power is just gone.
So a lot of Martinis' early work was basically like being a detective. He was hunting down the enemies of coherence. He and his team started systematically identifying all the culprits: tiny little fluctuations in temperature, microscopic defects in the materials, and all kinds of stray electromagnetic noise. Any one of those things could totally wreck a quantum calculation.
And that hunt really boiled down to this one central question that drove his research for decades. In a world that's just naturally noisy and chaotic, how in the world do you protect a quantum system long enough to actually do something useful with it? Answering that? Well, it was going to take a serious breakthrough. And that breakthrough, it brings us right to our third section, the transmon breakthrough. And let me tell you, this was not just some small step forward. This was a massive conceptual leap that made the idea of a large-scale quantum computer feel like a real possibility for the first time. You see, the first few generations of qubits were, let's just say, super finicky. So you had charged qubits, which were hypersensitive to any stray electric fields, and then you had flux qubits, which would get knocked over by the tiniest magnetic changes. Their coherence times were just a few nanoseconds. I mean, that's not nearly long enough to do anything useful.
But then came the solution. It was developed by a team that Martinis was a key part of, and it was this brilliant new design called the transmon qubit. It was just an incredibly clever compromise, designed specifically to be immune to the biggest sources of that pesky noise.
So, how'd it work? The single biggest problem was charge noise. The transmon design basically solved this by changing the qubit's internal energy balance. A good way to think about it is like tuning a radio. They essentially made the qubit's energy levels flatter, so it just couldn't hear all that charge noise anymore. It was a really brilliant hack of the underlying physics.
And the result? Oh, it was totally transformative. The coherence time, that's the little window of time you have to do your quantum calculation. It jumped by orders of magnitude. We went from a few nanoseconds to many microseconds. Now that might still sound incredibly short to you, but in the quantum world, that is an eternity. It was the difference between a science experiment and a real, viable platform for building a quantum computer. And that massive breakthrough set the stage for the climax of our story. Section 4, Google's quantum supremacy. So in 2014, armed with the power of the transmon, Martinis makes this huge move from the halls of academia to the corporate world of Google, with one single, incredibly ambitious goal in mind.
See, Google could offer Martinis something that no university ever could: practically unlimited resources and a laser-focused engineering mission. The objective was so clear and so audacious: achieve what people were calling quantum supremacy. The idea was to build a machine that could solve at least one problem that no classical computer on Earth, I don't care how powerful, could solve in a reasonable amount of time.
And to do this, they needed to build a processor with enough qubits to reach a level of complexity that you just couldn't simulate anymore. The target number they finally hit was 53, and they named the processor Sycamore. So what was this special task they gave it? It's a pretty abstract problem called random circuit sampling. Basically, you start all 53 qubits at 0. Then you apply a really complex random sequence of quantum operations that just completely scrambles them all up. The final pattern of zeros and ones that you get is incredibly difficult for a normal computer to predict.
And this is the punchline. The Sycamore chip did the task in about 200 seconds. Google's team estimated that for the world's most powerful classical supercomputer at the time, which was IBM's Summit, to do that same calculation, it would take 10,000 years. Now, there was some debate about that exact number, for sure, but the message was crystal clear. A whole new kind of computation had arrived.
The word supremacy itself was, well, it was controversial. A lot of people thought it was overhyped, but Martinisi himself framed it perfectly. This wasn't the end of the journey. It wasn't a computer that could solve every problem. No, it was a critical scientific milestone. It was the very first time that anyone had proven, with an actual experiment, that a quantum processor could go somewhere classical machines just couldn't follow.
And that brings us right to our final section, the architect's legacy. Because after hitting this incredible peak at Google, Martinis' story takes another interesting turn. In 2020, not long after that famous supremacy paper was published, Martinis left Google, and the reasons he gave really point to a classic tension you see in modern research. That pull between the open, collaborative culture of academia and the more proprietary, goal-oriented world of a giant tech company. After that huge milestone was hit, their paths just started to diverge.
But he didn't stop working. Of course not. He went back to his academic home at UC Santa Barbara and immediately turned his focus to the next set of grand challenges. The supremacy experiment was done with noisy qubits, remember? The ultimate goal is a fully fault-tolerant quantum computer, and that requires super sophisticated error correction. So he started exploring new architectures, improving efficiency, and, this is so important, training the students who are going to build the future of this field. So when you actually lay his career out like this, you see this really clear, powerful story. It goes from the fundamental physics of Josephson junctions back in the 80s to the absolute game changer that was the transmon qubit, to that massive industrial scale achievement at Google, and then right back to academia to tackle the next huge frontier of error correction. His journey basically traces the evolution of the entire field of superconducting quantum computing.
Which brings us to the core question that all of Martinis' work really leaves us with. We have now proven that this incredible computational power is real. So the question for us is, what should we do with it? Where should we point this revolutionary new tool to best benefit science and all of humanity?
This whole deep dive was based on the absolutely fantastic and detailed essay John M. Martinis, Architect of Superconducting Quantum Chips by Jörg Owe Schneppad. We seriously recommend you seek it out and give it a read.
Thank you so much for joining our Quantum Deep Dive. For more explainers and essays just like this one, make sure you visit schneppat.de.
Schneppat.de is a private project by Jörg Owe Schneppat dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.